I want to give full credit to Paige Miller. She just finished a master's degree under my supervision. Had the good fortune of landing a high quality conservation job with the San Diego Zoo in Southern California. So just relocated and isn't available now, though she wanted to be. I'll also point out that the management implications of the talk that I'm going to give together with Paige is on a poster there. So, so there's that. I hardly need to tell this group that trumpeter swans are North America's largest waterfowl. And you're also familiar with the very conservative Banco distribution, a minimum distribution of trumpeter swans based on the historic literature. And this group also knows that the Red Rock Lakes Wildlife Refuge, National Wildlife Refuge, was established in 1935 to rescue trumpeter swans from extinction. Now, the belief was that there were as few as 69 trumpeter swans left in the world. We know that wasn't quite accurate, that there were some in the far northwest, wintering coastally, etc. I'm not trying to retell that story to this group. What I want this group to appreciate is that there's no particular reason to think that somehow this was supreme trumpeter swan breeding habitat. This remnant, this relictual population persisted because of remoteness and because of behavioral attributes. So swans were able to overwinter there, and those swans that didn't overwinter were shot. So I think there is a form of artificial selection going on, and there is remoteness. But we shouldn't assume that because this is where trumpeter swans persisted, that this was somehow ideal habitat. This is a famous conservation story, and we're going to work right there. And the remarkable thing is that if you go from 69 trumpeter swans to, I don't know, 69,000 plus trumpeter swans, now you get to look at trumpeter swans at a level much more closely than you could in the past, when you had to treat every animal in such a precious way. Not that we don't treat them respectfully now, but we get to get up close and look. Now, this is imagery from a remote around-the-clock videography that we do. And over the years, I've exploited this technology a lot with sage grouse, and Paige and I applied it to trumpeter swans. Earlier, we applied it to trumpeter swans at Grays Lake National Wildlife Refuge. So here's a female settling in to incubate. I want you to think as you watch her. I want you to recall that incubation is an active process. This is not passive sitting on eggs. And she'll fuss and fuss here and get it just right. But this is an active process. The swan is investing enormously into these eggs. The other thing I want you to think about is what a peculiar mode of reproduction these birds have. What a strange thing to build a gigantic nest. What a strange thing to perch on top of it in a highly open environment and be exposed to the elements. Now, Red Rock Lakes is a high elevation, short growing season, cold, cold, cold. And what are you going to do? Build a giant pile and sit on top of it. This is strange, and we wanted to figure this out. I'm going to move on. She settles down eventually. So we know from previous work at Grays Lake National Wildlife Refuge with another former student of mine, David Bush, that swans are incubating all night based on videography, that their incubation recesses start and increase in frequency after sunrise, that there's a dip midday, and that there's a mid-afternoon peak, then or mid to late afternoon peak, and then swans cease with incubation at sunset, and then incubate again all night. We wanted to work this pattern out. What causes this, seemingly thermal pattern? And so that's what we looked into. Now, there are 4 mechanisms of heat transfer that matter for avian incubation, and I want to run through them really quickly. So the first one and most important is conduction. So conduction happens between the female and the egg. Primarily, the female is giving heat to the eggs, as you know, but the eggs can give heat back to the female. Also, there is a contact between the eggs and the nest. And so there is a pathway for heat exchange there. trumpeter swans are incubating with their gigantic feet. And that is the, primary mode of conductive heat exchange. I also asked, or we also asked, what in the world is this gigantic nest about? Does it have a thermal function? And I have to tell you, that I'm aware that birds are reptiles and reptiles are archosaurs and Anseriformes made it through the KT extinction. And I had dreams of glory that maybe this ancient crocodilian mode of incubation was persisting in swans. Is that gigantic nest a bit of a compost heap and generating heat and augmenting conduction? Newsflash, it isn't, but I'll get to it soon. Another important heat exchange mechanism is radiation. And radiation, the radiation that primarily matters is radiation from the sun to the eggs. So those photons hit eggs, and it's an important heat exchange. But eggs are a thermal body, and they also can give off energy, heat energy through radiation. The next one that will matter for us is convection. So convection is when heat exchange happens through a moving fluid. In this case, think of the wind blowing across the nest. And then the last one, and all of these are going to matter in the end, is evaporation. Evaporation is heat loss as water water vapor leaves the eggs. And so we found a cluster of swan nests in Red Rock Lakes National Wildlife Refuge, the place where swans were rescued. And we put up a weather station in the middle of that wilderness marsh, in the middle of the cluster of nests. And we measured precipitation, solar radiation, wind speed and direction, air temperature, and relative humidity. We also went to the nests and took evacuated swan eggs, either trumpeter shells that we could get or mute swan, and put eye buttons mounted on little wooden dowels inside the evacuated egg, and then patched over the hole and integrated those eggs into the nest like this. And so we had swans readily accept this additional egg. And so we had a measure of the actual temperature of the clutch, and that pink egg there would be our fake egg with a thermal device, measuring device, an eye button in it. And I want to remind you that we were doing videography on all of these nests simultaneously, so we knew exactly when the swans were on the nest or off the nest, and we were able to sync the behavioral data with the thermal data. We also positioned an eye button on the surface of the nest, so we knew how the nest surface was interacting with the environment thermally. And we buried an eye button into the nest body, so we understood the dynamic of the nest itself. Let's get to some results here. First of all, not surprisingly, but good to measure, successful nests had higher nest attendance than unsuccessful nests. Now, these are low sample sizes, but they were sufficient to detect a biological effect and with a significant p-value. And so nest attendance was greater in those nests that were successful, as defined by hatching at least one cygnet. And in fact, what you could see is that the recess duration for successful nests was shorter than unsuccessful nests. And there is a very, especially when you think of our sample sizes, a very, very strong trend, I'll say, about recess frequency. So successful females took fewer recesses, essentially, and certainly their recess duration was shorter. They were flat out on the nest more. We wanted to model nest attendance looking at environmental factors. And so we modeled it, sorry about that. We modeled it by logistic regression, but we used as our random effects nest ID. So these are essentially, it's the female, right? But technically we know it's the nest, but effectively it's the female. And we can't, and we're doing effectively repeated measures on a female. So we used that as a random effect and incubation day as a random effect. But our fixed effects were these things: air temperature, solar radiation, precipitation, relative humidity, wind speed, and wind direction, looking at the mechanisms of heat exchange that I've already discussed. Now I'm going to get to this complex figure more later, but the first result I want to show you is that trumpeter swans were very good at maintaining an egg temperature of 35.7 degrees C in the wild. Now this is a 1 day in the life of one female that we think characterizes what we were seeing. And it starts at midnight and it ends at midnight. And I'll remind you that the swans are incubating all night long. So we only attempted and only needed to model daylight incubation behavior, right? We already know without a model what they're doing at night. But I'm going to use this 35.7 degrees right now. Now, we expressed air temperature as deviation away from that that ideal temperature, and we squared it. Why would we do such a strange thing? Because it's not a linear relationship. As you move away from an ideal temperature, the temperature becomes more increasingly lethal to the embryo, right? Especially the heating. Think of the Scholander curve for the physiologists in the room. And we square it because it gives not only that exponential effect, but it makes going too hot or too cold a positive number, easily modeled. So this is what it looks like. Instead of just pretending in a biologically unsupportable way that deviation from ideal temperature would be linear, we expressed it in this curvilinear way. And we call that the relative severity of the temperature. We also fiddle around with relative humidity, and we did that very intentionally too. This is commonly done in these kinds of thermal models, and we express relative humidity as something called vapor density, the actual amount of vapor in the air. And the utility of that is that it quantifies water vapor independent of temperature, because we want to look at temperature and we want to look at the evaporative environment of the egg. And so really our final variables for our generalized linear mixed effects model were the random effects I've mentioned, and then these fixed effects that include air temperature deviation squared and vapor density. So then we did simple linear single factor models. For example, there's the air temperature deviation plus random effects. The random effects you would also know as a null model. And so on. So we did it again with solar radiation. And we did that for all of our random effects, just as single factor models, and used AICC to compare the models. So here's the null. And we found of the environmental things that we measured, 3 things mattered: deviation from ideal temperature, solar radiation, and vapor density. So now knowing that these single factors mattered, we looked at all of the variations of these single factors in multi-factor models and in interactive models. In other words, we're geeky people here like me, we concatenated it and came up with a suite of models. And many models were superior to the null model. But I want you to look at this top model here, which I will highlight. Long and short is that those 3 single factors, if you put them all in an interactive model together, and they are all in play at the same time in nature, this is what the female is experiencing, we end up with a very powerful model. In fact, it could take on all of the model weight. 100% of the model weight was taken by this interactive model with these 3 factors. So let's look at them. So deviation temperature, positive. The more the ambient temperature deviated from ideal, the more likely swans were to be on the nest. Makes perfect sense. What I want you to think about, though, is that the swans have to get on the nest if the eggs are going to get too hot. So don't think about incubation as just keeping eggs warm. A really important function of incubation in swans, we believe, is preventing eggs from overheating. This is also acutely the case with radiation. So when solar radiation goes up, the sun is shining hard at a high elevation marsh in Montana, those females get on the eggs. And then the most puzzling one to us was this vapor density, and it was a slight negative. So when vapor density would go down, swans were more likely to be on the nest. When the air got drier, swans were more likely to be on the nest. We also modeled the mound internal temperature. So this is the nest mound itself, not on the surface, on the inside. And we found when the air temperature went up, in this case, the nest got warmer, no surprise. When solar radiation went up, the nest got warmer. And when vapor density went up, the nest got warmer. So Really what's happening here is that the nest is acting as a thermal mass and it's taking on heat energy from the environment. That's not actually surprising. I just want you to know that we could show it. We also looked at the egg temperature of that fake egg that was in the nest. And you'll notice that we don't have radiation here. And the reason why we don't have radiation is that every time the female is on the nest, there's no radiation striking the eggs. And in an undisturbed swan, every time she leaves the nest, she covers the eggs and there's no radiation. So not surprisingly, air temperature and is positively associated with egg temperature, and vapor density is slightly positively. So the eggs could be picking up some thermal energy. All right, let's go back to this 24 hours in the life of a swan. Let's look at this now. So right here, whoops, I was going to do that. Right here is the ideal temperature, and you see swans incubating at that ideal temperature all night long. Sunrise comes and you get into morning and the swan takes her first incubation recess. So these kind of pink bars, those are incubation recesses. So this female got off the nest 5 times that day. Each time she gets off, egg temperature drops and she gets back on and she brings it right up back up to 35.7. She gets off, egg temperature drops, she brings it back up. This is not surprising, but it's a pretty good measurement. What I want you to look at next is the air temperature. So the air is cold, especially going into sunrise. The ambient temperature starts to rise. But notice that when you have these real peaks in ambient temperature, the female gets back on the nest. She's not taking her recesses when you have these pulses of heat. As you go into evening, the ambient temperature is warm. Typical high elevation mountain thermal dynamic. The nest temperature turns out is tracking the air temperature. I sure was hoping there was going to be a compost effect. And I looked at, we have some other data I can't show today, but it's not composting. It's a thermal mass. Let's look at solar radiation. You have to use the other y-axis here to see it. But when you see solar radiation spiking here, there's a spike, there's a spike, there's a spike. Those spikes happen, females are on the nest. This will matter for wildlife managers. If you're going to nests and you rush that female off the nest and she leaves with the eggs exposed, you're making those eggs vulnerable. And if you have a good pulse, like clouds leave, you have that sun shining down hard, those eggs are very vulnerable. They're picking up radiation, heat energy, photons from the sun. And it is a dangerous situation for the embryos, which of course, even when they're young, are floating on top of the yolk and are right on that top surface of the egg. Okay, now I'm going to add on this mysterious vapor density. And I have to say, it's hard to see the statistical effect on one day with one line, but you see that vapor density changes some through the day. And what we find statistically is that when vapor density goes down, swans are more likely to be on the nest. Now, we tried hard to make ourselves believe this was just a wind effect. Because you're out there and the upland winds come and they're warm, drying winds. And so the air over the marsh gets drier. And we should have been able to, I thought, if it was really just the wind, that it would be, we would get a wind effect. But vapor density is correlated with wind speed, but vapor density is the more predictive factor. And what I think is important to remember is that eggs aren't just losing heat when evaporation is high. And evaporation rate will be higher when vapor density is low, right? Because there's dry air. You can think of the interior of the egg as having 100% humidity and the vapor density being low. So the eggs are going to be losing moisture. So the eggs will be desiccating. Over a long incubation period, this could matter. Across a month of incubation, this could matter. And to our eye, nothing we would be able to pick up other than statistically, to our eye, females are very sensitive to this and they're defending their eggs against desiccation. They're defending their eggs against overheating. And of course, they're keeping their eggs warm when the external environment is cool. So in summary, in the end, successful swans are highly responsive to the thermal environment, the temperature deviation from ideal, solar radiation, and vapor density. Successful swans exhibit higher nest attendance than unsuccessful swans. We've seen this, for example, in sage grouse as well. Successful swans exhibit short duration incubation recesses. They have to get off. They have to engage in self-maintenance, certain amount of grooming, probably a little bit of eating, a little bit of drinking, and defecation, things like that. And then the last thing is that these large nests that they build, they probably have other functions like being above wave action, of course, but the large nests act as a thermal mass, but they don't act as a composting heat generator. Of course, many people were involved. I'm in particular going to call out, where'd he go here? There he is, Carl Mitchell, U.S. Fish and Wildlife Service, retired. He's back there. I could take your eyes out right now, Carl, with this pointer. But Carl opened the gateways for me to be able to do this wonderful work on swans in Idaho and later in Wyoming. So thank you very much, as well as all of these agency people that were so good, and other students in my lab at Idaho State University. Thank you for your attention.